Good morning, students. I welcome you all for AICT Prerana scheme, which empowers APST students to pursue their higher studies. Myself, Deepa, AP from UC Department, University of Engineering College. Today, I'm going to discuss analog communication. Under communication, first we'll discuss about what is communication. Communication is the process of conveying or transferring the information from one point to another. It also can be defined as process of establishing connection or link between 2 points for information exchange. The below one is the block diagram of the communication system. Therefore, the blocks present in this communication system are information source, transmitter, channel, receiver, destination. Let us discuss the function of each block in the next slide. Information source. Here, the message or information to be communicated is originated in the information source. The message may be words, group of words, code, data, symbols, signals, etc. The next block is transmitter. The main objective of this transmitter is to collect the incoming message signal from the information source and modify the signal to a suitable form that can be transmitted via the chosen channel to the receiver section. The next one is communication channel. It is nothing but a physical medium which connects the transmitter and the receiver. The communication channel may be copper wire, coaxial cable, fiber optic cable, waveguide, and free space or atmosphere. The next one is the receiver. The function of the receiver is to receive the incoming modified version of the message signal from the channel and process it to recover the original information. Next, we'll see signal. Signal is nothing but as a physical quantity which varies with respect to time or space or any independent or dependent variable. And it also can be defined as it's an electrical waveform which carries information. Below, the mathematical representation of the signal is shown, where A is the amplitude of the signal, as we are having the unit of volts, and omega is the field frequency, radians per second, and pi is the phase, radians. And the signal can be of two types. The first one is analog or continuous signal. The second one is digital signal. First, we'll discuss what is this analog or continuous signal. If the amplitude of the signal continuously varies with respect to time, or if the signal contains infinite number of amplitudes, then it can be classified as analog or continuous signal. The analog signal representation is shown in below figure. Next, we'll see what is digital signal. Okay, this digital signal contains only two discrete amplitudes. Then it is called as digital signal, and the representation is also shown. Here, this signal transmission technique is classified into two. One is baseband signal, another one is band pass signal. First, we'll see what is this baseband signal. If the signal contains zero frequency or near to zero frequency, then it's called as baseband signal. Example for baseband signals are voice, audio, video, biomedical signals. Whereas band pass signal, the signal contains band of frequencies far away from zero. Then it is called as band pass signal. Examples AM and FM signals. Next, we'll discuss what is modulation. Modulation is the process of varying the characteristics of high frequency carrier in accordance with the instantaneous value of the modulating or message signal. It's called as modulation process. Or it can also be defined as it is a frequency translation technique which converts your baseband or low frequency signal to band pass or high frequency signal. Okay, this modulation is carried over in transmitter section. This is the block diagram of modulation process. The first block is your message signal or modulating signal, and it is a low frequency signal. The another input signal you are going to give to the modulator device is the carrier signal, which is high frequency signal. These two signals are applied to the modulator. At the output of the modulator, modulated signal is, is coming out. Okay, after modulation process. So this is a tree diagram for your types of modulation. So the modulation is classified into two types. The first one is continuous wave modulation. The second one is pulse modulation. Under continuous wave modulation, again it is classified into amplitude modulation, angle modulation. Further, this angle modulation is classified into frequency modulation and phase modulation. Whereas in pulse modulation, it is classified into analog modulation and digital modulation. This PAM, PWM, PPM comes under analog modulation, whereas this pulse code modulation and delta modulation comes under digital modulation. These are the types of modulation. In this session, we are going to discuss continuous wave modulation. Okay, under continuous wave modulation, we are having three types: one is amplitude modulation, frequency modulation, phase modulation. Whereas this frequency modulation and phase modulation are grouped under angle modulation. Let us discuss the definition of these modulation. Amplitude modulation. Here, the amplitude of the carrier signal is varied in accordance with the instantaneous values of the modulating signal, whereas frequency and phase remains constant. In frequency modulation, the frequency of the carrier is varied in accordance with the instantaneous value of the modulating signal, keeping amplitude and phase constant. Phase modulation, phase of the carrier is varied in accordance with the instantaneous value of the modulating signal, whereas the amplitude and frequency remains constant. Okay, these are the definition of the three continuous wave modulation technique. Why we need to perform this modulation process? What are the benefits of this modulation process? Okay, the first advantage of this modulation process is to improve quality of reception, to avoid mixing of signals for multiplexing, to reduce height of antenna, to increase the range of communication, finally for flexible bandwidth. Next, we'll see in detail about amplitude modulation. Already we know the definition for amplitude modulation. I don't want to repeat it again. And this amplitude modulation is also known as double sideband full carrier. And so simply DSBFC. Okay, another name for amplitude modulation is double sideband full carrier DSBFC. Okay, now we'll see the derivation for amplitude modulated signal. The modulating signal is represented as EM of t is equal to EM cos omega nt. And the carrier signal is represented as EC of t is equal to EC cos omega ct, where EM represents the amplitude of the modulating signal in terms of voltage, and EC represents the amplitude of the carrier signal in volts. In modulation process, the carrier signal amplitude is varied, and it is given by the equation number 3. EAM is equal to EC plus EM of t. Now substitute equation number 1 and 2 in 3, you will get carrier signal amplitude changes. That is EAM is equal to EC of 1 plus EM by EC cos omega nt. But this EM by EC can be written as MA, that is called as modulation index. Now the equation number 5 is replace your EM by EC as MA, and the amplitude modulated wave is represented by equation number 6, that is EAM of t is equal to EAM cos omega ct. And now in the equation number 6, substitute equation number 5, you get your amplitude modulated signal in time domain. Equation number 8 represents the equation of the amplitude modulated signal in time domain. Now we see the amplitude modulated waveform. Here you can see three waveforms. The first waveform represents the modulating signal or message signal. The second waveform represents the carrier signal. And third represents the amplitude modulated signal. Let us discuss the frequency spectrum of amplitude modulated signal. Already we derived the amplitude wave equation. Now you multiply this EC and cos omega ct inside, and you will get an equation. as shown in equation number 8. Now use the trigonometric equation cos A cos B formula. Apply to the equation number 8. You solve, if you simplify, you'll get amplitude modulated signal having three terms. The first term is your carrier signal, EC cos omega CT, and the second term is the upper sideband, MAEC divided by 2 cos omega C plus omega M of T. And third term is the lower sideband, MAEC by 2 cos omega C minus omega M of T. Here, in the frequency spectrum, in this equation, you can observe three terms. The first term is carrier, the second term is upper sideband, third term is lower sideband. And it can be represented in frequency spectrum, the frequency spectrum of amplitude modulated signal. So in the frequency spectrum of amplitude modulated signal, two sidebands are generated. Okay, what is sideband? We'll see. The message signal is modulated by a carrier, creates the different signals at different frequencies. The frequency spectrum below and above the carrier frequency named as lower sideband LSB and upper sideband USB respectively. It is given in equation as FLSB is equal to FC minus FM and upper sideband frequency FUSB is equal to FC plus FM. The definition for bandwidth is difference between the highest and lowest frequency components in the frequency spectrum. It's nothing but the bandwidth. Bandwidth is equal to FUSB minus FLSB. You solve, you get bandwidth of the amplitude modulated signal as 2FM. Modulation index. Modulation index or depth of modulation is given by the equation MA is equal to EM by EC, and it can also be represented in percentage of modulation index. The total modulation index is expressed in percentage as percentage of MA is equal to EM by EC into 100. Next, we'll discuss about the derivation for modulation index of AM wave. For this, we are going to consider this waveform. By referring to the figure, we can write E max is equal to EC plus EM and G minimum is equal to EC minus EM. When you solve, you can get the equation number 15 and 16. And after substitution and simplify, we can get the final equation as MA is equal to E max minus E minimum divided by E max plus E minimum. And it can also be expressed in percentage of modulation index. Percentage of modulation index is equal to E max minus E minimum divided by E max plus E minimum into 100. And based on the modulation value, this modulation can be expressed in three different ways. If modulation index value is less than 1, it is called as under modulation. If modulation index value is equal to 1, it is called as critical modulation. If modulation index is greater than 1, it is called as over modulation. These are the three different waveforms for different modulation index values. The first one represents the under modulated waveform. Here, this modulation index value is less than 1. And the second waveform is the critical modulation waveform. Modulation index value is equal to 1. And third waveform is the over modulated waveform, whereas modulation index is greater than 1. Generation of AM wave. Two types of modulation techniques are used to generate amplitude modulated signal. The first one is low level modulation. The second one is high level modulation. In low level modulation, the carrier modulation is performed at low power level of the transmitter. Linear amplifiers are mainly used to amplify the AM generated signal. In high level modulation, the carrier modulation is performed at a high power level of the transmitter. At first, both carrier and modulating signal are amplified. Finally, modulation occurs in RF amplifier. Koala modulator. This circuit consists of three components. One is a nonlinear device, bandpass filter, carrier source, and modulating signal. Okay, these are the important elements present in this koala modulator. The circuit diagram for this is shown below. The modulating signal and the carrier signal are connected in series with each other, and their sum V1 of t is applied to the input of the nonlinear device. The nonlinear device may be a diode or transistor here. V1 of t is equal to x of t plus AC cos omega ct. And here nonlinear device is used to perform the modulation process. The input-output relationship of the nonlinear device is given by the equation 2. Now substitute the equation number 1 and 2. You can get the output waveform of the circuit. Here in this equation, terms 1, 3, 5 are useless. So we are going to eliminate that terms by using band pass filter. And finally, the output of the band pass filter will get only the modulated signal. Next modulator is switching modulator. Here the carrier signal is represented as C of t is connected in series with the modulating signal, which is represented as X of t. The sum of these two signals are given to the diode. The diode output is passed through the bandpass filter and the result is an AM waveform, which is given in equation number 1. When C of t is positive, V2 of t is equal to V1 of t. When C of t is negative, V2 of t is equal to 0. And finally, you get the amplitude modulated signal. In detection of AM waveform, detection is taking place at the receiver side. Demodulation or detection is a process of recovering the original message signal from the received modulated signal. The block diagram of the demodulator is shown below. And here we are going to discuss about three types of AM detectors. One is square law detector, envelope detector, rectifier detector. First, we'll discuss about square law detector. Here, the amplitude modulated wave is given as the input to the square law device. Here, the square law device also uses the nonlinear element for demodulation process. So, that is given the input-output relationship of the nonlinear device is given below. Here, when this is passed through the square law device, when the message signal is passed through the square law device, you can get the information signal as represented in equation number 2. In order to extract the original message signal, it has to be passed to the low pass filter. The low pass filter allow only the low frequency signal, that is your message signal. You get at the output of the low pass filter. Another type of detector is the envelope detector. The standard AM wave is applied to the input of the detector. In every positive half cycle of the input, diode is forward biased, which charges the capacitor C. When capacitor charges to the peak value of the input voltage, diode stops conducting. The capacitor discharges through R between the positive peaks. This process continues and capacitor charges and discharges repeatedly. In this way, the information signal is recovered. The another type is rectifier detector. The rectifier output is shown in this equation, shown as the equations. In rectifier detector, diode acts as the rectifier, which allows only positive half of the modulated signal to the filter. The low pass filter removes all the high frequency components and giving envelope at its output. This envelope will have some DC value which can be removed by passing through capacitor C. And finally, the rectifier detector output is envelope with zero DC value. Let us discuss the objective type questions. Consider sinusoidal modulation in an AM systems, assuming no over-modulation. The modulation index, which is represented as mu, when the maximum and minimum values of the envelope respectively are 3 volts and 1 volt dash. From the question itself, we can understand there is no over-modulation, means the modulation index is less than 1 or equal to 1. In such cases, the formula for modulation will be given by mu is equal to E max minus E minimum divided by E max plus E minimum. Substitute the given values and you'll get the modulation index. This mu is equal to 0.5 is the answer. Next question is 1 megahertz sinusoidal carrier is our amplitude modulator by symmetrical square wave of 100 microseconds. Which of the following frequencies will not be present in the modulated signal? A. 990 kilohertz, B. 1010 kilohertz, C. 1020 kilohertz, D. 1030 kilohertz. From the question, The frequency of the carrier signal is 1 megahertz. It's nothing but 1000 kilohertz. And the modulating signal is the square wave of period 100 microseconds. From that, we can find the frequency of the modulating signal as 10 kilohertz. Since modulation signal is symmetrical, so it means that it contains only all harmonics, that is 10 kilohertz, 30 kilohertz, 50 kilohertz. So that the modulated signal has Fc plus or minus Fm is equal to 1000 plus or minus 10 kilohertz. So you can get it 10 kilohertz and 990 kilohertz. Fc plus or minus 3 Fm, 1000 plus 30 kilohertz, 1030 kilohertz and 970 kilohertz. So 1020 kilohertz will not present. Next question. Consider the amplitude modulated AM signal, which is represented by AC cos omega CT plus 2 cos omega M of t cos omega CT. For demodulating the signal using envelope detector, the minimum value of AC should be 2, P 1, C 0.5, D 0. The modulated signal is given by the equation. So note that for envelope detection, the modulation should not go beyond full modulation, that is mu equal to 1. So amplitude of baseband signal has to be less than the carrier amplitude AC. So therefore AC should be greater than or equal to 2. Option A is the right answer. A message signal M of t is equal to cos 2000 pi t plus 4 into cos 4000 pi t. Modulate the carrier C of t is equal to cos 2 pi fc of t, where fc is equal to 1 megahertz to produce an AM signal. For demodulating the generated AM signal using an envelope detector, the time constant RC of the detector circuit should satisfy option A 0.5 millisecond, RC less than 1 millisecond, B 1 microsecond for less than RC less than 0.5 millisecond, option C RC for less than 1 microsecond, option D RC for greater than 0.5 millisecond. Solution for this problem is message signal is represented by the equation. It consists of two frequencies. The first frequency is omega 1 is equal to 2000 pi. And from that you can find your F1 is equal to 1 kilohertz. And from the your second frequency F2 is equal to 2 kilohertz. So maximum frequency is 2 kilohertz. Applying the formula, the option A is the right answer. Thank you.